Okay, so hello everyone. Welcome to LICD lecture number 40A. Today's lecture will cover analysis of ideal integrator in frequency domain, and we will be plotting the frequency response of the ideal integrator. Okay, so let us start. So ideal integrator circuit consists of a feedback capacitor between the inverting terminal and the output terminal, and we have a resistor R1 connected to the inverting terminal and it is connected to the V in. So this is my Opamp circuit for ideal integrator. It's very simple. So what the circuit will do, the circuit will integrate, right? So the output voltage will be an integral of an input voltage, and its equation is given by V out of t is equal to minus 1 upon R1 into Cf integral of 0 to t v in dt plus v out of at t equal to 0. So this equation we have derived it earlier while studying ideal integrator using Opamp before. This equation is in the time domain, as you can see over here. Okay, and if we apply a constant value to an integrator, let's say you have applied a positive DC value, you will get a negative going ramp. Why negative? Because of negative sign over here. And the integration time constant is R1 into C1, the product of R1 and C1. Okay, so let us proceed forward. So we need to analyze this ideal integrator circuit in frequency domain. So we need to find the transfer function for this system. That is, we need to find V out of S divided by V in of S. Okay, so if I take V out of S upon V in of S, it's a simple, it's looking like a inverting amplifier, similar to that inverting amplifier configuration. And for that, we know the gain is minus XCF divided by R1. Okay, so that is what we will write, minus XCF divided by R1. And what is XCF? 1 upon S into C1. Actually, it should be CF. By mistake, I've written C1. It should be 1 upon S into CF divided by the whole divided by R1. Okay. Now we'll analyze this a little further. So V out by V in will be minus 1 upon S into R1 into CF. Just let me put it in the full screen mode. Okay. Yeah, I think this is better. So V out upon V in the frequency domain is given by minus 1 upon S times R1 into CF. So this is my transfer function of my ideal integrator circuit, which is given by this, right? So this equation number 1 will will tell the gain of the integrator at all frequencies. Now, you put S equal to j omega in equation number 1, we will get V out of j omega upon V in of j omega is equal to minus 1 upon j omega R1 into C1. And if we take only the magnitude of it, it will be 1 upon omega R1 into CF, where your omega is 2 pi f and f is the signal frequency. So my gain of the system, that is the integrator, is given by 1 upon omega R1 into CF. Now, this let us call this equation number 2. Now, from equation number 2, we have uh, mod of A will be 1 upon 2 pi f into R1 CF. We can rewrite it as follows: 1 upon 2 pi R1 into CF into 1 upon F. And we can substitute 1 upon 2 pi R1 CF as FA. Okay. So the formula will become mod of A will be FA upon F. Okay. There is no particular reason why we are calling it FA. We can call it any other thing also, but just for notation's sake, FA will be given by 1 upon 2 pi R1 into CF. Let us call that equation number 3b. And if we take the logarithmic, it will be, the gain in logarithmic will be mod of A D in dB is given by 20 log to the base 10 FA upon F. Okay, so this we call it equation number 3a. Now, the above equations 3a and 3b tells us that the gain of the integrator depends on the frequency of the input signal. Okay, so that is very, very important, that the gain will be purely dependent upon the frequency, the input signal frequency. Okay, now let us go into LTspice simulation and let us simulate the circuit with some circuit values, that is with some values of CF and R1. So let me take you to LTspice. Okay, so here it is. Here we have considered build the ideal Opamp integrator circuit with the value of CF as zero point 0.2 microfarad and R1 as 10 kilo ohm. Okay, so the cutoff frequency will be given by 1 upon 2 pi R1 into CF. If you put this number inside the calculator, you will get as frequency value FA as 79.577 hertz. So one of you can cross check this. And now let me plot the frequency response curve for this. Okay, so here we get magnitude as well as phase plot. So here is my frequency response of this curve, of this ideal integrator circuit. So here, how do we calculate this gain over here? This gain, let us check how much is the value. So this is around 58.01, right? 58.01 dB. And how do we calculate it? So we can have this formula over here. Let me just push this aside. I think I should, yeah, I think it's clear now. So what we took is, we took the initial value of frequency as zero point 0.1 hertz, correct? So we know the formula, gain in dB will be 20 log to the base 10 FA upon F, and F we have considered to be zero point 0.1 hertz, and FA we have calculated to be 79.577. So if you work out in a calculator, this number will be 58.01, and indeed which we are getting also, it's 58.01 in simulation. Okay, now FA will be the frequency at which the gain will be around 0 dB. So let us check that. I'll right click over here. I'll adjust this till the gain becomes almost 0 dB. So here it is. I'll expanding it to make it very, very close. Okay, so this is very, very close to 0 dB, that is unity gain, and we are getting the frequency as 79.596. Yeah, 79.577, and we are getting 79.596. Okay, very close answers. Okay, so all this information we will get it from the frequency response curve. So frequency response curve will tell us how does the gain behave with respect to frequency. So as you can clearly see, at low frequencies the gain is high, and at higher frequencies the gain is reducing. Now let us check also one more thing, at what rate it is reducing. So this is at 10 hertz. Okay, close to 10 hertz. Yeah. Now let me check the other cursor and put it to 100 hertz. So if I change the frequency by 1 decade, let me see how much will be the change in the, yeah, I think I have to adjust this properly. Okay, I think that is fine now. Yeah, this is around 10, and okay, okay, yeah. So as you can see very clearly, let me just reduce this and make it close to that. Okay, so I am adjusting these values very clearly. So as you can see over here, almost like I think the frequency has been changed a little bit. Yeah. So if I change my frequency from 10 hertz to around 100 hertz, my change in the gain is around minus 20 dB. As you can see over here, almost close to minus 20 dB. So what it says is the roll-off rate at which the gain of the integrator, ideal integrator circuit falls is 20 minus 20 dB per decade. Okay, per decade. Why? because the frequency changes from 10 hertz to 100 hertz. That's why a decade change in frequency. So that's how we can plot this. And now let us analyze this further. So I just want to show you all that the same thing I have plotted on the in the OneNote PDF also. Let me show you all that first. Okay, okay, this is practical integrator. Let me open the ideal integrator one. Yeah. So over here, if we can see, this is the same plot which we have plotted over here. Yeah. So this is the same plot. Okay, as you can see over here, x-axis, y-axis, everything is same, and I've written over here the the gain and the roll-off rate and the frequency FA. Okay, so it's just similar to what we have got. Fine. So let me close this now and let us analyze this over here. And let me go to the full screen mode again. Okay. Okay, so this equation number 3a and 3b are very vital. They, with the help of these two equations, we can plot this frequency response curve. So from the frequency response curve, we will analyze this with the values of R1 and CF as 10 kilo ohm and zero point 0.2 microfarad respectively, and FA to be calculated with the formula 1 upon 2 pi R1 into CF, which comes out to be 79.577 hertz, and the gain in dB will be 20 log to the base 10 FA upon F. Here F we have considered to be around 0.1 hertz and FA is 79.577. So this number comes out to be 58.01 dB. And if we simulate this in LTspice, we get the following results. The gain over here at zero frequency will be 58.01 dB, which is very, very high. And the gate starts falling down at the rate of minus 20 dB per decade. That is also we have seen. And whenever the gain of the integrator is unity, what is the frequency corresponding to it? That is what we call it as FA. So that value, if you measure over here, it will be 79.6 hertz. So this is my frequency response of ideal Opamp integrator. Okay, now let us observe few observations. Let us comment on the few observations from this equation number 3a, 3b, and this figure number 1b, that is the frequency response. So we observe the following. At very low frequencies, at f equal to 0, the DC gain, that is the mod of A in dB, is very, very high. We have seen that it's around 58.01 dB. That's a very big number. So what will happen? At very low frequencies, the op-amp will saturate because the gain is tremendously high. This is because, now let us come back to the circuit. So what is the reactance offered by the capacitance? It is 1 upon 2 pi into CF, correct? So as the frequency is increasing, what will happen to the capacitive reactance? The capacitive reactance will keep on falling down. That is what we have written over here. At very low frequencies, F is 0, so DC gain is very high. So this is because the capacitive reactance given by XCF is equal to 1 upon 2 pi F into CF, which is very, very high at low frequency. So if we consider F is equal to 0, this XCF will be tending towards infinity, correct? And if this F is zero point 0.1, this XCF will be very high value. So what will happen? At low frequencies at F equal to 0, the reactance offered by the capacitance is almost like infinity. So the capacitor will behave like an open circuit. So at F equal to 0, C1 is behaving as open circuit. So circuit will look like this. So the as the CF is open circuit, op-amp will be in the open loop condition, correct? And in the open loop, we know that the op-amp has a gain of 2 into 10 raised to 5, correct? So now, even a small input offset voltage VIO or a bias current will be enough to make the op-amp go into saturation. That is, output will be either plus VSAT or minus VSAT. So this will lead to a DC voltage error at the output of op-amp integrator whenever the frequencies are very, very close to 0 hertz. Okay, so this second point is extremely important. It says that y at f equal to 0, the op-amp is working in the open loop and it is not working as a integrator. Okay, now third point is the gain that is delta A in dB of ideal Opamp integrator decreases with increase in frequency. That is very obvious. uh, from this graph, the gain decreases with increase in frequency. And why that happens? Again, because of the capacitive reactance. If your frequency will increase, your capacitive reactance will go on decreasing, right? So if the reactance go on decreasing, the gain will keep on falling down, because ultimately the gain is given by minus XCF divided by R1. So if XCF keeps on decreasing with increase in frequency, my gain of the circuit will keep on reducing. So that is what we observe over here. The gain of the circuit of the integrator, ideal integrator, will keep on decreasing over here. Okay. I hope this point is clear. Okay. Now the okay, so we have written over here, as the frequency increases, the gain decreases at a constant roll-off rate of minus 20 dB per decade. And this is because the capacitive reactance decreases as the frequency increases. Okay. Now, at F equal to Fa, so in this formula of equation number 3a, if I substitute F equal to Fa, what I will get? 20 log to the base 10 of 1, which will come out to be 0 dB. Correct? So what it says is, at F equal to Fa, my gain of the integrator will be unity. So let us observe this point. Yeah. So at F equal to Fa, that is 79.6 Hertz, the gain of the ideal integrator circuit is unity, or we can call it as a 0 dB. And we have explained this point, that is Fa and F are equal, so that means 1. So 20 log to the base of 1 will be 0 dB. And 0 dB indicates that the gain is 1 in magnitude. And how do we define Fa? Fa is the frequency at which the gain of the ideal integrator is unity, or 0 dB. And it is given by equation number 3b, which is given by 1 upon 2 pi R1 into Cf. Okay. I hope that that point is clear now. 1 upon 2 pi R1 into Cf. That is the equation which is given by. Now, what are the drawbacks, or why cannot we use ideal integrator in practice? Correct. So now let us see that. So gain, that is mod of that is A in dB of an ideal integrator is given by mod of A will be equal to 1 upon omega R1 into Cf from equation number 2. So for very low frequency input signal, or for DC, for which the capacitor CF will behave as an open circuit, the gain of the op-amp is very large. So due to this high gain of the op-amp might enter into saturation region, and the integration action might not be performed actually at lower frequencies. Even if no input is applied, Vin is equal to 0. Now this is the another drawback. Even with VL equal to 0, the input offset voltage and the bias current keeps the capacitor CF charging. Due to this, the op-amp will enter into saturation region even if we don't apply any VIN. And that is possible due to input offset voltage and bias current. So to overcome the above problems, we will go for a practical integrator circuit. Okay. So I think the objective of this lecture is over. We have seen how to plot the frequency response of an ideal integrator, what are its various features, and what are its few drawbacks. Okay. So that's it for this lecture. Next time we'll begin with the analysis of a practical integrator circuit in frequency domain. So until then, have a good day and thank you.